point. Thank you. Thank you, Bigly. Okay. Yeah, I is recording. Okay. So energy, muy importante. Quarter of the final. Very important for next semester. Let's go into it. Like I started last module, what I think I'm going to do is give you guys the entire equation content, and then the rest of today we'll be trying to get a feeling for, I know the symbols, but what does it mean? How can I understand this? And then lots of time on, all right, how do I apply it? How do I apply this to solve problems? Any remaining time today and in the days to come, we'll be practicing. We'll be learning by doing. So here are the 4 things. Wait, there are 5 things. There are 5 things. There are 5 things. There's a correction to this. Oh, right. Yes. Power is an additional thing we'll discuss. Power is, you'll pick it up fast. There's one more equation, but I really don't want to talk about it all in the same. Please do, if you are writing down these notes, please put gravitational potential energy. Potential energy is a category. Gravitational potential energy is a particular kind of energy. So we're going to learn about one form of potential energy. There are others. I will also, please note, you will also hear me referring to internal or thermal energies. There are lots of kinds of energy. There are equations for these. There's no equation for thermal energy. Well, just like there's no equation for normal, there's no equation for tension. Thermal energy, internal energy is going to be, if stuff goes missing, that's where it went. It's the eater of lost socks. Yeah. Okay. So you'll hear me refer to it. I don't have it on here. It's not a formula. Oh, and right, I was going to write down the formulas for you. Okay, please write this down in a separate section of notes, and then you go back and fill in the details for each, is what I encourage. This is all we're doing today. Making sense of these 4 things and applying them to as much as we can. They're also defined on the next slides, for what it's worth. But I think it might, I'm trying out, you should try out having them up front and then learning about them individually. MGY, yeah. McGee, MGY. Work, not weight. Yeah, very important, very important. This W is not weight. Whether it's weight or work is going to be very clear. We only use weight and force methods. We only use work and energy methods, and they're, as we will discuss, perpendicular methods. You don't do F equals ma in energy land. UG. U is what I will write potential energies as. Okay, good. Everyone got this down? Wait, no. Anyone want me to stay for on? Anyone need more time writing? Also, for what it's worth, I did post these slides for once. I've been bad about that. That takes me a while. Yeah, good, great. Okay, so what's the 1,000-mile view of energy? What is energy? What's the big dealio? First off, energy is an approach to physics. Energy and its sister momentum, which you'll do in lab to be exposed to it, but it's not nearly as important as energy, so I'm keeping it just to a lab. Energy and its sister, momentum, is sort of at right angles to forces. You can do a problem with force methods, or you can take a different perspective and do it with energy methods. Very, very many problems can be done both ways. That's really good news for you. If you pay attention and learn this technique, if you're bad at force, this can give you a way around doing force problems with force. You could solve all the force, many of the force problems in the force section of the final with energy methods, and I won't know the difference. If you get the right answer, you get the right answer. Likewise, by the way, if you know your force really well, you can do energy problems, many energy problems with. I will say though that when based on the problem, based on what is being asked, usually one method or the other is vastly easier. So yeah, I strongly suggest that you know both ways. Point two, the central idea of energy is conserved. Who's been told it's important to conserve energy? Really? No? Like 5 people? Really? No? Better conserve energy or it'll run out. Energy's a limited resource. You haven't been told that since you were babies? Okay. That's not what conservation means in physics land. To everybody else in the rest of the world, in English, conservation of some resource means it's limited, use it wisely because it'll eventually run out. To a physicist, conserved has a particular meaning, and that is it don't change. The total can't change. And if it does change, the amount of change is exactly equal to some external input or output. So, analogy time. Money in a market is conserved. Your bank account, you might have a checking and a savings. Wait, remember your guys' generation, you don't have either, right? You keep $5 under the... Anyway, too depressing. Let's pretend you have checking and savings accounts. Okay, so if your checking account goes down by $100 when you transfer it, what happens to your savings account? It had better darn well go up by $100 or you're going to be mad at your bank, right? The total amount when you transfer stuff around, when you shift money in accounts, total amount in your savings plus checking had better darn well be the same. If your net worth goes up by $38, that's because you got a paycheck coming in, right? An external agent is delivering some money to your system. $38, what is that? A week's worth nowadays, right? Yeah. So you got paid. The degree to which your bank account's total changes is exactly equal and always equal to how much goes in or comes out. That's this formula, by the way. Change in total, your bank account going up or down, can only happen because of total external works, total external forces doing something. Here's your paycheck. Your paycheck can change your total bank account. Otherwise, if you're not getting paid, if the external work is zero, if there's nothing external coming in or going out, change in energy is zero, man. Your bank account, your total account shouldn't change, can't change unless something is going in or out. Question, is the total energy still the same even if energy is transferred to another system? Very good question. If energy is transferred, one system must be doing work on the other. There is no transfer without work. Last point on this slide. Energy has many forms. With force, there's force, force, force. They're all forces. Well, they're different kinds of forces. No. Force, take it back. What's a good analogy here? Whatever. Okay, energy has many forms. They each have their own properties. We are focusing on 3. We are focusing on potential, gravitational potential, kinetic, and the transfer by means of a force work. That's it. That's it. That's all you need to know. If there's any missing energy at the end of the day, it's ended up as thermal, which is caused by friction. So they're the three listed on here. The three kinds, forms, things that you need to know are kinetic, work, and potential energy. And as I said, there's no formula. You will not learn the formula for friction, for thermal energy, internal energy. I will allude to it. Sometimes we will be able to calculate it based on how much is missing. Well, it must have gone there. But yeah. Okay. Let's chop. Let's chop. Strike this out. We have not been focusing on unit analysis this semester. I didn't check my slides and updating for the semester carefully enough. So you don't need to know that. The Newton meter squared per second squared. Kilogram meter squared per second squared. Here we go. Kinetic energy is half mass times speed squared. Please note speed, not velocity. We don't care about direction with energy. We just care about the total motion. Also note, energy itself is a scalar. What's scalar mean? You remember? It's been a minute. Scalar versus vector? Magnitude only. If you are moving versus if you are not moving, the more you're moving, the more kinetic energy you have. The less you're moving, the less kinetic energy you have. That's all there is to it. There is no such thing as 5 joules in the leftward direction or whatever. As I just said, the unit for energy is the joule, named after Mr. or rather Monsieur Joule, French guy. So yeah, kinetic energy is really pretty darn straightforward. It's the energy of motion. If you're moving, you got it. If you're not, if you don't have it, you don't. I don't have anything more to say about this now. Work. Work is more subtle. So listen up. Work is how energy transfers into or out of a system by means of a force. Again, this is an important idea. Work is energy flowing from or to a system because of a force. An external force is the ones we care about. So energy can slosh around inside a system in various forms. Internal energies, the total energy of a system can go between becoming kinetic, various forms of potential, thermal, whatever. But if you want to increase the total energy, you got to have an external force doing work. I keep using the phrase a force doing work. Please note that you can calculate the work of any force, just like torque. Remember we did torque? We said this force does this torque, that force does that torque, the other force does the other torque. You can calculate the work done by any force. We will only ever calculate based on external forces when you have simple objects, but yeah. Force times displacement, delta x is change in position, times the cosine of the angle. Force, for this to be used, it better be a number, not a function. So that is to say, if force isn't constant, you have to use the area under a graph. We didn't talk about springs, did we? We didn't, right? We didn't. I'm not forgetting this. We didn't talk about springs, so we're not even going to do this. MCAT students, there's a big thing about springs. MCAT likes to ask about springs. You will use this idea on MCAT, but I'm not going to spend time on it here. Stick around after class and I'll give you some extra info about that if you're curious. The last point is perhaps the most subtle. What is theta? Theta is the angle between force and displacement. So I'm cutting this trig down to its bare bones in this class. You only need to know the cosine of 3 angles, and there's a way to cheat and get around it. First, here's the 3 angles. If force is parallel, if theta is 0, I should say cos is 1. If work is anti-parallel, cos of 180 is -1. So work becomes negative. And if force is perpendicular to displacement, cos of 90 is 0. So there are the only cosines that you have to know. And there's a way to cheat, which I encourage you to do. Think about this for half a second. If a force is pushing me in the direction of motion, it's giving me energy, right? That's the first case. Force is parallel to the displacement. It's helping me. It's trying to speed me up, for instance, give me more kinetic energy. So if the force is parallel, work is positive, energy is going up. Change in energy is work done. If work is positive, change in energy is positive, yeah? If force is pushing back against the direction of motion, is that force helping me? That force is hurting me. That force is taking energy out of my system. So if force and displacement are anti-parallel, that work is negative. Energy is being removed from system. If force is at right angles to displacement, normal force of ground on me compared to my motion rightward, was the normal force helping me? Was the normal force making me move? No. So work is 0. That force isn't doing anything to your motion. Might be, normal force is helpful because I'm not falling through the building to the first floor, but I'm not saying the normal force is 0, but I'm saying it's doing no work. It's not changing my energy. Let me emphasize again, this, what I'm about to say is just change in energy is equal to external work. If work is positive, what's happening to your energy? What's the change? The change is positive. So what does it mean for a change to be positive? Energy is increasing. If force is anti-parallel, we get a negative work. If work is negative, what's happening to your energy? If force is perpendicular, that force is not doing anything, to energy anyway. Work is 0. If change in energy is 0, or energy is not changing. The energy might be cycling forms, but it can't be, total energy can't be going up or down. Okay, so with that caveat, you can condense this equation to force times distance and insert the appropriate sign, or make it 0 if the force and the direction moved, or if that force isn't helping the direction move. So if people say force times distance, sure, I'll take it. Just remember to include the sign, plus, minus, or kill the term entirely, make it 0. Questions? This is subtle, but also very important. Work is central to all this. Yeah. Well, if your calculator's in degrees mode, you should put it in degrees. If your calculator's in radians mode, you need to use radians. Look what mode you're in. But, and this is a big but, I'm only asking you these 3 things. I won't ask you to be doing cosine of 30 or whatever. Cosine of 150, I guess. Okay, I'm going to skip past the example. I want to lay out the puzzle pieces and have you start to put them together in a second. Kinetic energy is motion. Work is interactions, exactly like some other law that we discussed. Didn't we say force is mass times acceleration? Acceleration is your motion quantity in Newton land, and force is your interaction quantity in Newton land, right? F equals ma is to say energy is only changed by work. F equals ma, delta E equals total W is the same theme in different languages. I do want to emphasize, I've just described kinetic energy and work. There are many forms of energy. We'll discuss them. We'll discuss them very soon. You can do a hecking lot with only these two things: energy, kinetic energy, and work. You could say, how does this, that, or the other change if there's only one form of energy, kinetic energy? If you've got a simple system with a point particle with no friction, whatever, the only form of energy you've got is kinetic. We'll see an example of this again once I get through the core and we hit examples. I said this. I'll say it again for emphasis. Total energy, if you don't have external forces on you, is conserved. There's no change. Final equals initial. Delta equals 0. Initial equals final. Since what I just said also, simple systems, very simple systems, don't have internals or potentials. The only form is kinetic. So if total energy don't change and energy is just kinetic, then you could say initial kinetic equals final kinetic. Does that mean for a simple system that velocity can't change? Let's write this down. If 1/2 mv initial squared equals 1/2 mv final squared, is it possible to change a velocity, still have the same kinetic energy? Assume mass doesn't change. That's changing the system. So if you've got vi squared equals vf squared, cancel, cancel. Does that mean vi equals vf? Is there any way that the square of a number can equal a square of another number without the numbers equaling each other? Hey! Yes. For instance, if you've got a kid bouncing on a trampoline, the bounce, if the bounce doesn't absorb energy, if ultimately if the trampoline springs don't heat up, if they're very elastic, then the speed of the kid just before they strike the trampoline will be equal to the speed with which they leave. In lab, you will be playing around with carts. If you have equal mass carts coming in and bouncing off of each other, you should actually be able to see that the initial kinetic energy of a cart and the final kinetic energy of the cart don't change if they're bouncing straight off each other. They exit at equal speeds, opposite directions, opposite velocities. Does that make sense? Yeah. If the velocity just switches sign, if you just turn around, that's not changing your kinetic energy. Here's another example: Earth orbiting the sun. Gravity's doing no work, right? Gravity's at right angles to the motion, no work. So kinetic energy doesn't change. Does that mean that we have a constant velocity? No, no. If the Earth had a constant velocity, we'd fly off into deep space. The Earth has a steadily changing velocity. What is changing about the velocity? The direction. We go in a circle. Okay. Nope. One last thing. One last point. Come on. It crashed. Oh, no, it didn't crash. I'm just a big silly, big silly who didn't write the last slide. And I discovered this at the 3 o'clock class and then just forgot it. Gravitational potential energy, as I promised. Hey, what's m times g, by the way? What's mg? I mean, seriously, mass times field is weight. What's y? What did I describe y before earlier? Did I? Distance up, vertical height. Hey, hey, hey. So I've got a force times a distance. That looks a lot like a work, doesn't it? Actually, all potential energies are intimately related to the work of a force. Every potential energy has an associated force, and sometimes it's useful to consider that force as an external work, and other times it's useful to consider that that force as part of your system and call it a stored potential energy. I will give you an example of this in 20 minutes. Sometimes we consider, for instance, gravity is the one potential that we're doing this term. Sometimes we'll consider gravity external and say we got work done by that force. Sometimes we'll consider it internal and say there is a stored gravitational potential energy. And which way you do it is your choice, but often it's vastly easier one way or the other. Is good? There's not much to gravitational energy. If you're up, you got more of it. If you're down, you got less of it. Here's one thing though. What happens if I dig a well? What's my y? Negative. Mg times negative is negative, right? Remember, g is not a negative number, right? G is the magnitude 9.8 meters per second squared. The acceleration is negative g. Doesn't mean g is negative. Okay. As I banged on for like an hour in module 1. So if you are underground, y is negative. What does that mean about the sign of u? Can you have negative energy? Yes, you can. Energy does not have to be positive. Kinetic energy, mass is always positive, v squared is always positive. Kinetic energy is always positive, but it is perfectly legal to get negative potential energy. Ultimately, negative potential energy just says you're below the reference point. You're below wherever you define y equals 0. But that's a where you set y equals 0. That's just your choice as a problem solver. You could set y equals 0 here. You could set y equals 0 there. You could set y equals 0 at mean sea level. You could set y equals 0 at the first floor. You could set y equals 0 at your mama's height. It doesn't matter. As long as you're internally consistent, problems are, nothing changes in the problem. Okay, that's all of the theory. Now let's learn to apply it. This will be like 4 problems, I think. So problem 1, find the work done that Max does on Maya and Sled. There was a confusion in the 3 o'clock section. I'm going to emphasize that Max is one little bunny. He's 15 kilos. Maya is sitting on a sled, and when I say combined mass, I mean Maya and her sled are 20 kilos. That 20 kilos is disjoint from Max's 15, okay? She's not 5. Okay, ready, set, go. You have all the pieces to solve this. Ready, set, go. Put this in question B, by the way. Google form B. What the what? Radians per second squared? What? Hey, what are the units of work? What must they be? Joules. Don't just tell me a number. Tell me that number, joules. Yes, Michael. Okay, 1 minute. If you're confused, you can ask a question, but don't just leave it blank. That means you fell asleep. No credit. Highly. No. Mass isn't part of work. All right. You guys are paying attention. A quarter of the 3 o'clock class got stuck in this, and I wasn't sure why. Much happiness. I love that when people get stuff. We are asked for the work. We use the work equation. Work equals force, displacement, the cos theta. What's the force? What's the displacement? What's cosine of this angle? 300. 300 what? Good. Okay, this is the work that Max does on the sled and sister. Follow-up question, how much work does weight of Maya and her sled do as she moves? So question C, there is a weight force acting on Maya. You can calculate that. How much work does that do? Find the work weight, the weight work. Okay, you already know the equation. You already solved one. Plug in, chug in. If I'm asking for the work done by a force, you can just use the formula for work. I'll show you how to use potential energy later. "30 seconds. Give me your best shot or ask me a question." Someone asked, I'm confused. Do I take the weight of the whole system? And the answer is, that depends on what I ask. If I asked what work is done on Maya, use Maya's mass. If I asked what work does weight do on Max, use Max's mass. If I asked what work does weight do on the system, you'd use the total mass. But it depends on what I ask. I specifically asked, how much work does the weight force on Maya do on her as she displaces? So use her mass. Sydney, displacement is the same as the previous. I'm going to consider different forces. Yeah, please. what I said was it depends on how I ask it. And what I asked specifically was find the work done by Maya's weight force on her as she moves. So consider Maya is the object of study. Which direction is he pulling her? Point. Make up a direction. Which direction is she moving because of that pull? What's the angle between those two directions? Okay, the angle between rightward and upward is 90. The angle between rightward and rightward is 0.
So he's not, okay, he's just like pulling like, not like this. Like, you know how when you sometimes pull something and it's heavy?
The pull is parallel to the ground. He's moving along the ground. Attention to detail. Okay, time's up. Let's scan the results. Okay, and half of you got it. Let's plug into the equation. We're going to calculate the work done by weight, WW, U. Okay, what's the force? Mass times field of her, that's about 200 newtons, right? What's the displacement? She moves 25 meters, great. What's the angle? I only asked you to know 3 angles. What's cos of 90? You think about this for a second. As I said, you can cheat on these. If you think about what energy means, is gravity helping her? Is gravity helping her move? It's level ground. Is gravity slowing her down? Is gravity stopping her motion? Gravity is neither of those things. The work done by weight must be 0. Don't forget to account for that. If you're perpendicular, that force does nada, nothing. Work done by weight equals 0, because the displacement and the force are at right angles. That force is not what moves her. Weight force is not 0. Weight force is 200 newtons. I said the answer is 0. I said the answer is 0 because weight force is perpendicular to which way she moves. Is that always true, by the way? Is weight force always perpendicular to direction of motion? How can weight force not be perpendicular to motion? I moved up, I moved down. My displacement positive, negative. Hey, which sign is work when I go up? Which direction is my displacement? Which direction is the force? Cosine of 180 is -1. What's the sign of my work? What's the sign of my work? Negative. Force downward, displacement upward, work is negative. Can I think of that in any other way? What is gravity doing to me as I rise? Am I not slowing? Gravity is sucking energy out of me. As I fall, which direction do I move? Which direction is the weight, force? Is gravity helping me move? You betcha. Gravity's why I fall. Gravity's cosine of 0 is +1, so I get positive work, so my energy increases. I speed up as I fall. We should do another problem. I'm talking too much. Someone yawned. Maybe it was me. What form of energy What must be increasing? What form of energy is taking it if Maya is moving at a steady speed? We're on flat ground. He's exerting a force on her. She's not accelerating. Where must his work be going? Question 4. Question D. Suppose as he pulls her, she's not speeding up. He's pulling her at constant speed. He's exerting 12 newtons, but she's moving at a constant speed. What form of energy must be taking his work? He's doing work on her system. She's the system. He's doing work on her. But her kinetic energy isn't increasing. What gives? Where must that be going? Yeah, work coming in. Something's got to happen to the energy. What kind of energy? Take your best shot. It's got to go somewhere. What did I say is the culprit when we have missing energy? Thermal! Why isn't she speeding up? There's got to be another force, right? What force keeps her from speeding up? What's friction do? Friction causes thermal energy to increase. Friction, the work done by friction becomes internal thermal energy. Remember I said, we don't have an equation for this. We don't need an equation for this. But I do have the idea that if there's energy going away, missing energy, it's always going somewhere. And I would say it's going into internal energy. Look at the runners of the sled. They are slightly heating up. It's hard to notice this because, ice is cold, but with an IR camera, maybe you could even see the runners heating up a little. Now, part E, follow-up question E. Next question E. Put this in E. Suppose there's no friction on her. He's exerting 12 newtons on her, and she's speeding up faster and faster and faster. What's her final speed? Don't use force and kinematics. Use energy. Find her speed after he moves her 25 meters. Just with energy. La question is, now pretend there is no friction on her. So that means she has to speed up. He's applying 12 newtons. She has to be accelerating. Find her velocity at the end of the 25 meters of distance. Brittany, no kinematics. No kinematics for you. Do not use kinematic equations. You could solve this with force and acceleration and kinematics. I want you to use energy. Hint, her energy is going into motion form. Don't you have an equation relating motion energy to speed? Another question I need clarification on. Someone asked, is her velocity the same? The same as what? I need clarification. The same is a comparison. Please resubmit with more details. I don't know, I am confuzzled. Okay, great. Hint. There's energy coming in. How much energy comes in? How much energy is being delivered by external works? 300 joules, right? That's what we just calculated. Is anything going into internal forms? No. I said frictionless. There's no increase in thermal now. So 300 joules is coming in. What form does it take? Hint. She's speeding up. It's motion energy. So you've got 300 joules of kinetic energy. Solve for V. Okay, so I got clarification. Asking, is her velocity the same as question B? We didn't solve for velocity in question B. The work done on her is the same as in question B. The work on her doesn't change. You know the force acting on her, you know the distance acting on her. The work is the work is the work, 300 joules of work. Whether she speeds up or not depends on whether energy can be sucked into internal form if there's friction, or whether it has to stay kinetic. So many correct answers. Okay, here we go. So as per the hint I just gave, what kind of energy do we have? How much is there of it? 300 equals, what's the kinetic equation? Mass, what is the mass that I should use? Y20. If I'm asking about her kinetic energy, her velocity, use her mass. Yeah, times V, maybe I should say V final squared. Okay, solve. 20 divided by 2 is 10. 300 divided by 10 is 30. V final equals squirt 30. 5 and change? 5.5? Sure, I'll believe that. Units? You're yeah, is good, comrades. For every problem you ever do that's more complicated than just here's a velocity, calculated kinetic energy, for something where we're using energy methods, don't go, by the way, we got one more to do. For anything we're using energy methods in, you always have to ask yourself this question. What kind or kinds of energy do I start with? What kind or kinds of energy do I end with? What forces, external forces, are doing works on me? Change in total equals external work. Bang, that's it. You're done. That's all there is to it. Now we're going to apply that to another system, and it's the same process. Ask yourself what form or forms of energy we start with, what form or forms we end with, write an equation, you're done. I will give a hint here. You can consider gravity in two ways. You could think of gravity as an external force doing work on you. You could consider gravity as an internal force storing potential energy. Use the second one. It's easier. Trust me. Talk about why after you solve the problem. No, you don't need the mass. You don't need the mass. It's like Martin Luther. You don't need the mass. Y'all were quiet before, now you're being silent. Who's stuck? Okay, so here's the process. What are the initial energies? What are the final energies? What are the works? Apply the equation. What are the initial energies? What kind of energies do we start with? Potential. Anything else? Are you moving? No, right? I said I start from rest at a height. Great, so write down that equation. What is the equation for potential energy? And I'm going to say y is going to change, so I'll say y initial. M doesn't change unless the writers throw up. Any other form of energy, or is this the total initial? What about the final? Now you're down. You're at the 3-meter height. What kind or kinds of energy do you got? This should not be hard. Is it moving? You betcha. Is there height energy? Yes, a little. That's it. That's all the forms of energy that we've got so far. And if it's a frictionless track, there's no internal. There's no disappearing. What's the kinetic energy formula? What's the potential energy formula? There we go. There's the internal, initial. There's the final. Now we just need to consider external forces doing work. What forces act on the ride? What is this? A roller coaster. Wait, do we need to calculate his work? Nope. The hint that I gave at the beginning was you could consider gravity in one of two ways, either as an external doing work or as an internal storing potential. The hint was do the potential method. We're already accounting for gravity. You don't need to calculate his work. It's already done. What other forces act on sucker? No, in the Google form. Tell me all the forces that act on the sucker, other than weight. In the Google form, name for me, this is question G, name a force, name the forces that act on this roller coaster cart other than weight force. G, F is for the final answer for the speed. Okay, so again, the question for G is what force or forces other than weight force act on the cart as he's rolling down the hill? This is question G, not F. And in particular, I'm asking about forces, not energies. Also, motion is not a force. Also, centripetal is a result of forces, it is not a force itself. You can go back to the list on day one of forces if you wish. Weight, normal, friction, buoyancy, thrust, drag, spring, tension. Those are the only possible answers. Okay, let's discuss. Is there tension? Why not? No rope. Is there friction? Why not? Because I said so. Is there drag? No, why not? Because we never include drag in this class. Is there normal? Yes. Oh, now we got to think about something carefully. How much work does the normal force do? 0. Very good. Why? Normal force is defined as being perpendicular to the surface. Displacement is, it had better darn well be along the track. Displacement and normal force are at right angles. What do we know about work done by right angle? Cosine of 90 is, so no work. Yeah? Is it always true that normal's never going to do no work? How could normal do some work? Well, I like that. Pushing a sled, or if you're moving along the surface and right angles to the surface, they're still perpendicular. Pushing a sled, you're exerting a normal force on the sled. Or for that matter, what manner of force, I hope I don't regret this, what manner of force is this folder exerting on my iPhone? It's a normal force. Did it do a work? Didn't you see this guy move and fly through the air? Yeah, it just delivered some energy. Normal forces can do work, but not if you're sliding along the stationary surface. Okay, so what do we conclude about the work done by external forces? There is none. What's the energy, the master energy equation? Change in energy is work done. That's it. Okay, so I've got the final, I've got the initial. What's the change? How do I get change from final and initial? What's delta even mean? Initial from final, yeah. Final minus initial. So we write down the final expression. Oh, for dog's sake. We subtract off, and we set that equal to the total work. How do I solve for VF? How do you solve for VF? I solve for VF by simplifying first. First thing I do is I notice that every term has an m. What can I do if every term has an m? Yeah, divide both sides by m. What do I get? A simpler equation, that's what I get. Here, let me copy this over the next slide. Okay, so if I divide by m, what do I get? Okay, now next thing I see to simplify is that I got g times this and g times that. Is there another way I can write that? Combine like terms, what would I get? So I would turn this into, wait a second, yf minus yi, what is that? Delta y is just changing height. Oh, hold on. I want to get VF alone. Let's get rid of the fraction. What do I multiply both sides by? No, I want to get VF alone, so I do. Oh, my sweet baby Newton. You recognize this formula? I wrote V initial in there for the lols to trigger your memories. Final velocity squared minus initial velocity squared plus 2 times acceleration times change in position. That is the energy equation. He's just in disguise. So I didn't freak you guys out on the first day. Third day, but whatever. Yeah, you see? Okay, let's finish off. How do I get VI alone? VF alone. Uh-oh. Square root of a negative number? Can you do that? What am I lying about? Which way are we going? We're going down. What's delta y, positive or negative? What happens if you have negative times a negative number? We're not taking the square root of a negative. If you start at rest and try to go up, your initial velocity would have to be square root of -1 meters per second to move up from rest. But we're going down. Delta y is negative. Negative and negative is positive. Square root is real. Pluggy any, you done. Square root -2gy. Delta y is -2 times 10 times, what is delta y here? -22. You're going down by 22 meters. What's that become? 440 square root 440 is 20? Am I right? Bang. You cannot solve this problem with force methods. The acceleration is a very wildly changing function based on the track. You guys don't know how to handle those changing accelerations or even how to calculate them in the first place. Energy, let us get this in one equation. Once you know what the initial and final energies are, it's bang, bing, bang, zoom, you're done. You'll see that. There will be many examples. Theoretically, I could do that problem if I knew the shape of the track with force methods, but it'd still be ugly. It would cause me much pain. Energy methods like that. Okay. I think that's all. Go home. Love you all. Bye. Question?
I just figured it out, and then I just put that into the K and then did the kinetic energy equation.
That is exactly equivalent to what we just did. Yeah. Yeah.
Thank you.